this section, we'll be looking at a variety of different functions and how to graph them. So let's get started. Our first function, one that you're familiar with, g of x is equal to 0.5x minus 3. And this comes from something we're very familiar with from Algebra 1, y equals 0.5x minus 3. This is what we call the slope-intercept form, and we call it that because this number, the 0.5, is the slope, and this number is the y-intercept. Okay, so this one can be very easy to graph. We're going to start with the y-intercept, which is -3 in this case. So I'm going to put my x-axis up here. And then -3 would be right here. So that's the beginning of my graph. And then the slope is 0.5. So slope rise over run, I go up 0.5 and over 1. To make it a little easier to count, I'm going to double both of those and say 1 over 2. So up 1 over 2, up 1 over 2, and so on. And we know this is a linear equation, so we're going to have a straight line just like this. Pause your video and work on checkpoint 1. In our next example, we'll be graphing a piecewise function. And this is what the function looks like. Start with our curly brace. The first part is x plus 1 if x is less than or equal to 2. And then negative 2x plus 7 if x is greater than 2. So I'm just going to draw a little dotted line here at 2, because this is where we're going to change functions when x is 2. Okay, I want you to notice that this rule includes 2, and this rule does not include 2. It's important in a piecewise function that no number of the domain is included in more than one part, because then we wouldn't have a function. Okay, so let's look at this first part, x plus 1. I've got a slope of 1 and a y-intercept of 1. So I start here and go up, slope of 1, and this is for less than or equal to 2. So when I get to 2, I put a solid dot there to show that that's included in my answer. Now the second part, negative 2x plus 7, I count up here 2, 4, 6, 7, there's my y-intercept, and it's got a slope of negative 2. So down 2 blocks for every block it goes over. And I'm drawing this as a dashed line because this is not really part of our function. We haven't gotten to 2 yet. Now once we get to 2, then we can make our line solid. And I erase this part that was just helping me get my line straight. Now these two pieces happen to meet at that point, but that doesn't always occur. So just be careful about where you put your solid dot. If these two were not meeting here, I would have to have an open dot on this piece. So let's pause the video now and work on checkpoint 2. In our next example, we're going to work with another piecewise function that both pieces are linear, but it does look a little different. Okay, this is our function, f of x, and the first part is x plus 1, and that applies if x is less than or equal to 3. So you can see it once again. We've got the equal bar here, and that 3 is going to belong to that first piece of the function. And then we've got negative x plus 8 if x is greater than 3. Okay, so I'm going to move the x-axis up just a little bit. And now we'll look at the first function, x plus 1, slope 1, y-intercept 1. So starting here, slope 1. And this rule goes all the way to 3. And then it stops there. My second function has a y-intercept of 8 and a slope of negative 1. So starting from my x-axis, 1, 2, 3, 4, 5, 6, 7, 8. And then the slope, negative 1, is going to go this way. I can do better than that. And you see here that these two functions do not intersect. Now the second one only applies when x is greater than 3. So I'm going to erase this part in the first 3 blocks. And then this piece needs to be marked with an open circle there to show that it goes all the way up to 3, but it does not actually include the number 3 in its domain. Okay, and then this one continues on this direction. This one goes this way. And that is my piecewise function. Pause the video now and work on checkpoint 3. In this example, we're going to graph the absolute value function, which is a special kind of piecewise function. And in the checkpoints, you'll be graphing transformations of this absolute value function. So we could say f of x is equal to the absolute value of x. But I could also write this as a piecewise function. Say that f of x is equal to x if x is greater than or equal to 0. So if x is positive or 0, then we're going to just graph y equals x. And then we'll graph y equals negative x if x is less than 0. So those are the two pieces of the absolute value function. Okay, and I'm going to turn this into a 4-quadrant graph. So this is y, this is x right here, And for x greater than or equal to 0, so I make a solid dot to show that 0 is included, and there's my graph. For the second part, when x is less than 0, we use negative x. Well, if x is negative, then negative x is going to be positive. And so this piece will go this direction. So this is the absolute value function written as a piecewise function. Pause your video now and work on checkpoint 4. In this example, we'll be looking at a real-world situation that can be modeled with a piecewise function. Okay. You may understand that for many different kinds of utilities, there's one rate for one level of usage, and then if you start using more of that utility, you pay a higher rate for the excess. And that's what this problem looks like. So, it says the Birmingham Waterworks charges its residential customers with a 5/8 inch water line a basic service charge of approximately $25. So I'm going to write that down. Basic service, $25. Okay. The first 1,500 cubic feet costs about $2 per CCF, so 100 cubic feet. So I've got 2 CCF. Well, let's write it this way. $2 per CCF up to 15 CCF. Okay, now here comes the extra charge. To encourage water conservation, excessive water usage is charged at a higher rate. It costs about $4 per CCF for a CCF above 15. So we're going to say $4 per CCF after 15. Okay. And first we're going to answer a couple of questions about just what is the bill, so that you can kind of get an idea of where we need to graph. So the first question is, what is the bill if there's no water used? Okay, so if I use no water, I still have to pay the basic service charge, but I don't pay either one of these. So my basic service charge means I have to pay $25. And then if I use 1,500 cubic feet, I'm going to pay the $25 service charge plus $2 for each 100 cubic feet. So 25 plus 30 gives me a bill of $55. Okay. Part C, how much would it cost to use 2,500 cubic feet of water? So for 2,500, I'm going to take a little shortcut. I know for 1,500 my bill's $55. And then after the 1,500 cubic feet, I had another 1,000 or 1,000 cubic feet. Okay, so 10 times 4 gives me another $40 on my bill, so $95 for 2,500 cubic feet of water. Okay, Now they ask us to find a rule for the function, and we're going to graph that rule as well. I can actually combine these first two statements into one rule. So I'm going to write f of x is equal to, and in the first place, I'm going to pay $25 whether I use water or not. So 25 plus $2 for every unit of water. And this is good for x less than or equal to 15. And then the second part of my rule, I'm going to pay 25 plus the 2x plus 4. But I can't say 4x because I've already paid for 1,500 cubic feet. So I'm going to have to say x minus that first 1,500 cubic feet if x is greater than 15. So this is my function rule. Okay, let's take a look now at what this graph would look like. I know that if x is 0, I'm going to start at 25. So on my vertical axis, I want to make sure that 25 is on there. And I want to make sure that my x-axis has 15 on it, but not 15 right at the very end. I want to go out beyond that. So I'm going to go as far as 30. And on the y-axis, I'm going to go up by 20s. So we'll start with 20, 40, 60, 80, 100. This is the money. And then here is the volume of the water. And again, I want to make sure that I go up as far as 15. So let's go up by 2. Not 17, 18 here. And 15, I'm going to put a little mark there to remind myself that that's where the function is going to change. Okay. For 0 gallons of water, I'm still going to pay $25. So that's there. When I use 1,500 cubic feet, I said that my answer was going to be $55. So at 15, I want to be at 55, which is just below the 60. So right about there. Okay, and then after that, this was a slope of 2. And now I'm going to have a slope of 4. So I'm going to figure out for 20 CCF, I would have 25 plus 2 times the 15, plus 4, and 25 minus 15 would be the 10. So we had 25 plus 30 plus 40, so 95 at 20 units of water, so just below the 100 mark. So this is the graph of my piecewise function for this water bill calculation. Pause the video now and work on checkpoint 5. Another function that often has business applications is the step function, where we charge a certain amount for one item, and then when the weight or the size of the item gets to a certain level, we charge another amount. Okay, and it doesn't go up on a regular basis like a linear function. It goes up by a set amount when we reach a certain limit. This is called a step function because it looks like a set of steps going up the graph. So let's take a look at one that's called the greatest integer function. Okay, greatest integer function is written this way with brackets around the x. And what that means is I take x and I chop off the decimal. I don't round it off, I chop it off. And whatever's left is the value of my function. So for instance, f of 0 would be 0. F of 0.5 would also be 0. F of 1 would be 1. F of 1.2, also 1. F of 1.999, also 1. Because I just chop off the integer and that's the value. So to graph a greatest integer function, I'll start here at 0, 0. And for the x equals 0 all the way up to 1, but not including 1, the value is 0. So I'm going to make an open circle here and draw a line between 0 and my open circle. Now the value is 1, beginning at 1 and going all the way up to 2, but not including 2. Okay, so here you can see the first little step. The next step would start at 2 and end just before 3. And you continue on in this way, solid dot on the left side of the line, open dot on the right side of the segment. So this is the greatest integer function. And like I said, many applications in the business world. So pause the video now and work on checkpoint 6. Now that we've defined what a step function is and drawn its graph, let's look at a real-world example that uses a step function to figure postage for overseas shipping. Here's the problem. To ship a first-class package to Brazil in 2016, the U.S. Post Office charged a fee of $13 for the first 8 ounces. So $13 up to 8 ounces. $9 for an additional 24 ounces. So $9. 24 more than this would be, we're going to say plus $9, up to 32 ounces. And then $20 more for a maximum of 64 ounces. Well, this was 22 for up to 32 ounces. And then I have to add $20 to that, up to 64 ounces. Okay, so my weight is going to be on the x-axis, and the charge is going to be here. So the 22 and 20 is going to be $42. So my y-axis needs to go up to 42. My x-axis needs to go to 64. So I'm going to make the x-axis go up by 8, and I'll just mark every other one to kind of keep it a little bit neater. So 24, 32, 40, and another 16 would be 56. And I'll put the 64 in there since that's where we're going to end. And then on the y-axis, we need to go up to $42. So let's go up $5 per square. And that will keep us on this graph. Okay, so $13 up to 8 ounces. So here's $13. And this step is going to be, I guess we could leave an open circle here, because if I have no weight, I'm not shipping a package, so it wouldn't be included. If I'm shipping anything at all that has weight, it's going to be $13. Then my next step is going to be $22 because I'm paying the extra $9 up to 32 ounces. So here's 32 ounces and here's $22. And I begin this step where the last one left off. And there's that step. And then the last step, I had $20. So now I'm at 42. And that starts at $32 or 32 ounces. So here's 32 ounces. And again, if it's exactly 32 ounces, I pay the lower rate. If it's over 32 ounces, then I have to pay the $20 more, which is 42, not 32. Okay, so 32 ounces, $42. Open circle here, closed circle here, and I would assume that if it's over 64, that probably some other rule is applied. But there's our step function for postage for packages sent to Brazil. Pause the video now and work on checkpoint 7. Let's look now at the graph of a square root function. Here's my function. G of x is equal to the square root of x minus 1. And I might know that the square root function would look something like this. Let's say when x is 4, y is 2. When x is 9, y is 3. So this is my basic square root function. But what happens to it when I put the minus 1 inside the square root? Okay, if I'm not sure, I can always make a table of values and find out. So let's make a table of values. And we see that if x is 1, then I've got 1 minus 1, 0, and the square root is 0. If x is 2, 2 minus 1 is 1, and the square root is 1. If x is 3, 3 minus 1, so this is the square root of 2, which is approximately 1.414. And we're going to skip 4 and do 5. If x is 5, then I'd have 4, and the square root of 4 is 2. And then if x is 7, I would have the square root of 6, which is approximately 2.449. And we'll do one more. If x is 10, I'd have the square root of 9, so that value would be 3. So now I've got some points. At 1, I'm at 0. Okay, at 2, I'm at 1. At 3, I'm at 1.4. So right about there. At 5, I'm at 2. At 7, I'm at just under 2.5. So right about there. And at 10, I would be at 3. So this is my graph for this function. And you might notice at some points on this graph, this is a difference of 1. This is a difference of 1 in the x. Here's a difference of 1. Here's a difference of 1. So this -1, we could say -1 moves 1 unit to the right. Let's look at another piecewise defined function. Here's my function, f of x equals, first piece, x squared if x is less than or equal to 2, and square root of x minus 1 if x is greater than 2. Okay, and I'm going to put this again on I'm going to move the y-axis over a little bit so we can see a little more of the function for x less than or equal to 2. This is a parabola. We know that this parabola has a vertex at 0, 0, and it's just our basic generic parabola. So I'm going to put the vertex here. I know I'd have a point here, a point here, and then a point up here. On the positive side, I'll have a point here, mirror image, a point here, not here, over here at the 2, and I stop because it says x less than or equal to 2. So this is all of the parabola that I'm going to get for this one. And now I have to use this function for x greater than 2. Well, this is a function we just wrote. So let's think again. When x was 2, this was 1. And we put an open circle there because it says x greater than 2. X equals 2 is up here in the first function. Okay? And then when x was 5, we got a value of 2. So this is 2, 3, 4, 5. There's that. When x was 3, we were at 1.4. So I can put that point in there just to have one more little point to graph with. And there's our square root function from 2 onward. Okay, so here's a piecewise defined function that has some nonlinear pieces. Now that we've had a chance to graph several different types of functions, Let's look at some graphs that we might find in a magazine or online and see what information we can get from them. This figure shows the median sales price in thousands of dollars of new privately owned one-family houses by region of the United States. The regions being Northeast, Midwest, South, and West for the years 2008 to 2015. Our first question is, how do prices in the West compare with those in the Midwest over the period shown in the graph? We look first at the prices in 2008. The prices of the houses in the West started out approximately $100,000 higher than those in the Midwest. In both regions, prices declined initially, but by 2012, the prices had rebounded, and the gap between the two regions shrunk to less than $50,000. By 2015, the gap had widened again to about $75,000. Another question we might ask is, which region typically had the highest prices? We can see here that the Northeast had the highest median sales price for all of the years shown. Let's look at another graph. In this graph, the average price f of x of a barrel of crude oil in dollars in year X is shown in the figure for the years 2005 to 2015, with projected prices shown through the year 2025. First thing we're asked to do is to estimate the function values f at 2015 and f at 2025 and interpret the answers. To do this, we start by drawing a vertical line at 2015. We then draw a horizontal line from the point where this vertical line intersects the graph, and we see that the price at this point was about $50 a barrel. For the year 2025, we repeat the process. Draw the vertical line first, and then draw a horizontal line from the end of the vertical line back to the Y scale. This shows us that in 2015, the price of oil is projected. This shows us that in 2025, the price of crude oil is projected to be about $80 per barrel. Our next question is, during what period did oil prices drop below $40 per barrel? To answer this question, we draw a horizontal line at the $40 level. We then look for a place where the graph drops below this line, and we see it right here in 2016. Okay, another question is, at what time was the price over $100 a barrel? We use the same process, draw a horizontal line at 100, and then see where that line intersects our graph. The first intersection point is here just before 2011, so toward the end of 2010, and then the graph drops back below 100 about midway through 2013. So we could say from late 2010 to midway through 2013, the price of oil was above $100 per barrel. In our last example for this section, we're going to look at the vertical line test. The vertical line test is a quick, easy way to determine whether or not a graph actually represents a function. And the rule of the vertical line test is this: if a graph is a function, no vertical line will be able to cross the graph in more than one place. Let's look at a couple of examples. Here I have a graph. I don't know whether or not this graph represents a function, but what I'm going to do to try to determine that is to draw some vertical lines and see if I can find a vertical line that would touch the graph in more than one location. So I can look at the grid lines and see that none of them touches the graph more than once. And I can draw some other vertical lines in here and see that none of them are going to touch that graph more than once. So this particular line is a function. Let's look at another. Suppose I had a parabola that was kind of laid over on its side. Is this a function? Well, you can see that many grid lines intersect the parabola both at the top and the bottom. So this is not a function. This concludes this section. You should be ready now to work on your math lab assignment.